Okay, good morning, everyone. Welcome back to class. It's the 15th of October here, so we're in week 9. We're well into the second half of the semester here. So remember, Thursday, no class. It'll be fall break. So we'll have today's class, and then we won't meet again until the 22nd. Okay, so the second exam is all graded. You should be able to find your exam in Canvas. I put the key in Canvas as well in an earlier announcement, so you can check your grade and everything. And just let me know if you have any questions on the score you received. The median was about 80%, so half of you guys got a B or higher, which I think is good. All right. So are there any questions here as we get back into chapter 4 here? Anything you want to go over real quick? So let's see. So again, fall break on Thursday, Friday this week, and then exam 3 will open in about 2 weeks, and that will cover chapter 4. So pretty much got 3 days here to finish up chapter 4. Should have plenty of time to do that. Good. So where were we? We, towards the end of class, did this activity where we were calculating X bar, the sample mean, and we did it for 3 different sample sizes, uh, ranging from small to larger, although even 3 is pretty small. And what we saw is that as we increased the sample size, X bar became relatively bell-shaped. Okay, and so that's an important takeaway. It says that the mean of the sampling distribution for X bar will be the same as the mean of the parent population, but the spread will decrease. It gets smaller, so the standard error for X bar is given by sigma over the square root of n, and then the shape becomes normal. Okay, so this is the result that we're seeing here, the mean and standard deviation of the sampling distribution of X bar. Okay, it's similar to the result for the sampling distribution of p hat. So it's the second time we've seen sampling distributions. It's based on the central limit theorem. Okay, so super important here. This forms the foundation for using the normal distribution for making confidence intervals and doing hypothesis tests for quantitative data. So super important idea here. Okay, so so we did a couple of applied problems here where we're using the normal distribution. And now we really want to do inference. So we'd like to be able to use X bar as a point estimate from mu to create a confidence interval. So let's think about how that worked in the previous chapter. In chapter 3, remember we had p hat. That was the confidence interval, right? And the central limit theorem told us that p hat has a sampling distribution that's approximately normal, right? So we had a approximately normal standard normal distribution for p hat, right? And then that allowed us to create a confidence interval. So we went p hat plus or minus a critical z-score times the standard error for p hat. So that formula was p hat 1 minus p hat over n. Okay, so that's chapter 3 stuff. So the idea here in chapter 4 should be, oh, and remember the z-score. So the z-score for p hat would be p hat minus p over the standard error, right? So p 1 minus p over n. Okay, so chapter 4, we'd like to do the same thing. So we saw that p hat, X bar is also normally distributed if certain conditions are met. So central limit theorem also applies to X bar, so that's good. So you're thinking, well, let's do the same thing. Let's create a z-score, right? So that would be X bar minus mu over the standard deviation or the standard error of X bar, which is sigma over the square root of n. Okay, and so if that's your plan, if that's your idea, then that's correct. But there is a problem here. And the problem is we don't know what sigma is. Okay. If you're trying to figure out what the mean is, then you almost certainly don't know what sigma is, what the spread is, right? So that's a problem. And so what we do is we do the next best thing. We estimate sigma by using the sample standard deviation. Okay, when you take a sample, you will have a sample standard deviation, right? And so we can use S to estimate sigma. But statisticians pretty quickly realized, mathematical statisticians from the 20th century pretty quickly realized that this actually leads to other problems. Okay, in fact, we lose the z distribution altogether, and what it creates is another distribution. Okay, it's called the t distribution. Okay, and so if you have sigma, if you somehow know what sigma is, then the confidence interval for mu truly is z star sigma over the square root of n, like that. Okay, that's the margin of error formula. But again, we typically don't know what sigma is. So what we do is we estimate sigma with S. And like I was just saying, that unfortunately loses us the z distribution. We drop out of the z distribution and we go into a new distribution called the t distribution. Okay, so we do have a formula for the confidence interval and we'll use it, but we need to talk a little bit about the t distribution first. Okay, so it's very, very similar to the confidence interval for P in chapter 3, but there's a new twist here, and that is we have a new distribution. It's the t distribution. Okay, so we need to talk about that t distribution a little bit. The good news is that it is very similar to the normal distribution in a lot of ways, so it's not really going to computationally be very difficult for us to use, but we do need to be aware of some of the theory behind the t distribution first. Okay, so that's the idea, and so the formula is here on the formula card. Okay, it's right here. So it's the one sample t confidence interval for the mean. Okay, so so it's a point estimate plus or minus a margin of error. So there's much here that's similar to chapter 3. So yeah, let's talk about that t distribution. So so the t distribution, probably the most unusual aspect to it is this thing called the degrees of freedom. Okay, like I was telling you earlier, stats is filled with all of these unusual terms, quirky sounding definitions. The degrees of freedom is simply a parameter that describes the precise form of the distribution. Okay, it's related to the sample size. Okay, so in fact, there's a formula for it. The degrees of freedom is simply 1 minus the sample size. If you remember the formula for the sample standard deviation, it's been a while, but remember we had that curious n minus 1 in the denominator. It's a very similar idea. Okay, so that degrees of freedom there equals n minus 1. It's basically telling you how large the sample size is. And while the t distribution is always bell-shaped, it actually is slightly different for every sample size. Okay, so as the sample size increases, S as an estimate for sigma improves, and the t distribution thus becomes more and more like a normal distribution. Okay, so that's different. The normal distribution doesn't really change for each sample size, but the t distribution does. Okay, so let me try to help you think about that. So the t distribution, much like the standard normal, is centered at 0, and it's bell-shaped. Okay, but it tends to be thicker in the tail of the distribution. Okay, remember the normal distribution approaches the x-axis very quickly, and very quickly it becomes basically indistinguishable from the x-axis. But the t distribution tends to be a little bit thicker. It just goes out a little bit further before it converges to the x-axis. Okay, so it's a little bit thicker in the tails. And like I was saying, it changes for every sample size. So the larger the sample size, the closer it approximates a normal distribution. So this diagram is it's kind of busy and there's a lot going on here, but I think it's very useful. So this dotted line actually represents this standard normal curve. So z, right? So that's the standard normal with mu 0, sigma 1. So the dotted red line, we just wanted to say, to emphasize that it's different than the t-distribution. So we made it dotted. And then those other solid lines, the black, the blue, and the green solid lines, those are each one of those is a different t-distribution. Okay, so we have 3 t-distributions, one with 5 degrees of freedom, one with 10 degrees of freedom, and then one with 20 degrees of freedom. Remember, degrees of freedom equals n minus 1, so it's related very closely to the sample size. And so for 5 degrees of freedom, that's basically sample size 6. So it's a small sample. 10 degrees of freedom would be a larger sample, sample size 11, and then 20 degrees of freedom would be sample size 21. So we have 3 t-distributions ranging from a very small sample of, say, 6 up to another, a larger sample, but still kind of small, degrees of freedom 20. Okay, so which one is which? Well, the green will be the furthest away from the normal distribution. Okay, so when you only have 5 degrees of freedom, which is sample size 6, you don't have a really super accurate estimate for sigma. So it creates more variation in the tail. So it's much thicker over here than the dotted line, right? So if you see the dotted line out here on the right, the green line is well above that dotted line, okay? And that's because it's a small sample t-distribution, okay? And so we can tell here, because it's the tallest in the tail and the shortest at the peak, that this has to be the 5 degrees of freedom t-distribution. Okay, so if it's thicker in the tails, well, that means there's more area in the tails, which means there's less area for the middle. So the peak will be shorter and the tails will be wider. Okay, and that's because it's coming from a small sample size and the estimate for sigma is a little bit poorer there. Okay, so then what's the next one? Well, the next one up would be the blue line, right? So we see that it gets taller in the peak. And then if we look at the tail here for the blue, it's kind of subtle, but you can tell that it's converging to the x-axis faster. Its tail is not as thick as the tail for the green 5-degree freedom t-distribution. Okay, but it's not as tall as the black line here, right? The black line is even taller at the peak. So that means that this blue one here is the 10 degrees of freedom. Okay, so you're getting the idea. So as the sample size increases, the t-distribution will change. And if the sample size is large enough, if there's enough degrees of freedom, then the t-distribution actually starts to converge to the z-distribution. Okay, so what would the third one there be? Well, the third one is this black line here. And we can see that its peak is not quite as tall as the dotted z distribution, but it's pretty close. And if we look out in the tails, yeah, it's a little bit thicker, a little bit taller than the standard normal, but not too much taller, right? So it's still a little bit thicker in the tail than the z distribution, but it is starting to converge there. So that would be our 20 degrees of freedom. So that's one key idea about the t-distribution, okay? So it changes for every sample size. So the larger your sample, the closer it becomes to the standard normal. Okay, so that's one idea. The other idea is that it's bell-shaped. Okay, so that's similar to the normal, and it is symmetric about 0. So it's centered at 0. Okay, so there's some here that's new and some that's the same, right? Okay, so what do we need to be able to do with this t-distribution? Well, if you see the formula here, to get our confidence interval, to get our margin of error for that confidence interval, instead of a critical z-score, we need a critical t-score. So how did we get the critical z-scores? Well, we used GeoGebra to do that. So we'll do the same for the t-score. We'll use technology here to get us our critical t-scores. So let me show you how to do that. The directions are here in the lecture notes. We also have videos for all of the GeoGebra stuff on our YouTube channel. So you can feel free to watch that if you need some extra help on that. So let me show you how to do it. So so this example comes from the textbook. This is example 4.17 in the text. We have a t-distribution with 4 degrees of freedom, and we want to find basically the 95th percentile in that distribution. Okay, so we want to find the value such that only 5% is above that value. So it's the 95th percentile. Okay, so it is computed to be, and we'll cover that up, pretend like we don't know what that is. Okay, so so how would I proceed? Well, just like with the normal distribution, I'll usually draw a bell-shaped curve. Okay, by hand, it's really hard to get something, you know, to distinguish between a z and a t distribution. They're very similar in appearance. So it looks like a normal, but in my mind, this is a t distribution. So it'll be centered at 0. And when we were doing, say, a 90% confidence interval, we would have to go out, you know, a certain distance such that we capture the middle, you know, 90%, right? Okay, so it's a very similar idea here. So how far out in this distribution do we have to go such that only 5% is above that value? So where is 5%? Does that look like about 5% of the distribution to you guys? Yeah, I could probably go a little bit to the left or a little bit to the right, but that certainly is reasonable. So that's our critical t-score here. So you can use t if you want, but the t star tells us we're probably doing some kind of inference, right? So how far out do we have to go? Well, if there's 4 degrees of freedom, and degrees of freedom is n minus 1, what does that tell us about n? This is coming from a sample of size 5. Okay, so we don't really need to know that for this, but just to give you an idea, this would be if you're taking very small samples, say of size 5, and you want to use the t distribution. Sometimes we are stuck with small samples. So how would we proceed here? Well, we'll go to GeoGebra, we'll go to the t distribution, and then we would put in 4 degrees of freedom. So if we want 5% above, we would go above, and then percentages, remember, proportions are on the outside, and then values in the distribution are on the inside. Okay, so that's how we would find this. So let's go ahead and do that. Oh, I thought this was the t distribution. Why are we going to student here? Well, it's an interesting story. You might want to read up on it, but basically, the very quick version of the story is the guy who invented or first formulated the t distribution was working as a quality control statistician at the Guinness Brewing Company, so the beer company in Dublin, Ireland. And he wasn't allowed by his company to publish the results, his results from his research, because it was a trade secret. So he published anonymously, and he called himself the student of another famous mathematician. So it's sometimes called the student distribution or the t distribution. So anyway, if you see student distribution or the student t distribution, it's the same as the t distribution. Okay, so anyway, let's go ahead and open up GeoGebra here and get a little practice with this. So, all right, so we're going to go to GeoGebra. I'm going to hit the toggle, 3 dots, probability calculator. We've done this lots of times, so I think it'll be pretty natural at this point. So if we're in the t distribution, we'll go to distribution, and then we look at this dropdown. Okay, so if you enjoy this class and you're interested in doing maybe statistics or data science or data analytics, you'll take more stats classes, and in those classes you'll learn about all of these different distributions, the chi-squared, the F, the exponential, etc. There's tons and tons of these distributions. Okay, so in our class we do to kind of three distributions, okay? But mostly it's this normal or the student, okay? So we'll go to student. And so again, you can see it looks bell-shaped. Maybe you can tell that it is a little bit thicker over here in the tails. Anyway, so once you're in the student t-distribution, then you put in the degrees of freedom. And for this example, there were 4. And we said we're trying to find the critical t-score such that 5% of the distribution is above it. Okay, so there we go. It's the same graph that I drew on the other page, except theirs looks a little bit better. And so the value coming out of here is 2.1318. Okay, so the value that shows up right here is 2.1318, which is the value that is calculated in that example of the textbook. So if you are reading the book, you can find it there. Okay, so you guys try one. This one also comes from the textbook. This is the very next example in that book. So let's pretend like we don't know the answer here. So you want to find the t star, the value in the t distribution. Of course, we need to know how many degrees of freedom. It's related to the sample size. So this would be coming from, say, a larger, but still small sample of only 19. And we want to find the value that has only 2.5% of the distribution below it. Okay, and there is a table for the t-distribution, but I wouldn't even recommend using it. I would just go right to GeoGebra. If you want to see the table, I can meet with you after class and we can work on the table, but it's not nearly as accurate as using software. So you'll want to draw the t-distribution, put your 0 in there, and then I'll let you do the rest. You want to get a graph that approximates what that part of the distribution looks like. Okay, so I'll just go quiet for maybe about 3 minutes here and wait for you guys to chime in here with the answer. If you'll just put it in the chat, then we'll go through it together. So let's see, we want to go out in the distribution such that we only have 2.5% below. Okay, so I'm going to come down here. I'm going to say, oh, that looks like about 2.5% to me. So that's 0.025. And then so our t-score will be this value here. Okay, so how many degrees of freedom? Well, there's 18. So we go to the student t-distribution. And then we want to have less than, and we want to have about 2.5% below that. Okay, so the value we're looking for will be here. Did anybody get it? Great, that is exactly right, Armand, thank you. Perfect, yeah, so about negative 2.1. So we'll go 18, we'll go less than, and then 0.025. And yeah, of course it's negative because we're in the left end of the distribution and this is symmetric at 0. So yeah, negative 2.10. And that is the value that we find in that example in the textbook. So negative 2.10. Okay, so why are we learning about calculating t-scores? Well, it's going to do the same thing that z-scores did for the confidence interval. Okay, so for the confidence interval in chapter 3, we use z-scores, right, to create our margin of error. Now here in chapter 4, we're going to use t-scores to calculate the margin of error. Okay, so it's very analogous, very similar, but you know, there are some differences. So we're actually ready now to jump into the t-distribution. Okay, so so the formula is similar. We have a point estimate instead of p hat, it's now x bar because this is quantitative data, plus or minus a margin of error. So the margin of error, just like in chapter 3, will be a critical score, in this case a t star value, times the standard error for the for the point estimate. Okay, so it'll be a t star critical score times the standard error. Okay, so with that in place, let's go ahead and try one of these. So the lecture notes for this section are great, but I kind of prefer doing things in a slightly different order. So I'm going to skip over some of this and I'm going to jump down here to page 126. Okay. I just think it just works better to do this first and then go back and do a sample size problem. So what we have here is, well, hopefully, I think you guys are aware of these. I think they might even still do these commercials, but you know, back like in the 90s, they you know, they had these commercials all the time where there was this owl, right? And the owl would say, well, how many licks does it take to get to the center of a Tootsie Pop? I think they're still around. So these commercials. So you know, Tootsie Pops right there. So it's a candy sucker, and at the middle of the sucker they have various types of candies, right? And so one of the more popular ones is the chocolate at the center. So it's kind of cool, right? So it's a sucker, but then you also get some chocolate. And the question that the owl asks in the advertisement is, you know, how many licks does it take, right? And so so amazingly, there's actually real data about this. There were some, at least a couple of statistics classes that had students that volunteered to put together this data set. So they're out there on the internet, and you can look at this data. And I think there might have even been another example where somebody built a machine to simulate this sort of thing. But anyway, so this is real data, and there were 92 volunteers. And so each volunteer gets one of these chocolate Tootsie Pops, and they counted the number of licks required to get to the center. So it's kind of a quirky data set here, but it's a real data set. And so everybody did this, right? And they just counted and they wrote it down. And so, you know, maybe the first person 90, right? The second person 400, third person 200, right? So just imagine 92 numbers, each one is a count. And then so that's quantitative, right? We have quantitative data here. And so the parameter of interest is not P in this case, it's mu, right? In chapter 3, it was all about the proportion, right? But now it's the mean. So the average number of licks required to get to the center. So we don't know what that is because nobody, because it's impossible to know that, right? That we would have to basically destroy all the product by testing it out, right? So nobody really knows what mu is, but because of these classes that actually put this data set together, we do have an estimate, right? So our one best number is x bar, right? So that is the point estimate, okay, for the number of licks required to get to the center. Okay, so a way to think about this is another number line. Okay, so certainly it can't be below 0. You can't have a negative number here. What's the right end? You know, who knows? But certainly it wouldn't be more than 1,000, right? So I think we can all agree it's definitely less than 1,000. So who knows? Maybe mu is down here. Okay, so mu is, definitely more than 0 and almost certainly less than 1,000. And so to build a confidence interval, they actually got a data set, right? So they had 92 volunteers, so n is 92. And then they found their x bar, right? So x bar, because of sampling error, is almost a little bit certainly off of mu, right? So it could be a little bit above or a little bit below, we're not sure. So they have the x bar in the middle. Then, as you guys know, we're going to build a confidence interval. So we're going to put a margin of error on the right and a margin of error on the left, right? So we build a margin of error on the right based on the t-distribution. So go out to the right, and then we take the same distance, the same margin of error, and we put one on the left, right? So we add and subtract that value from x bar. Okay, and so we hope that the interval captures the parameter mu, right, to estimate mu. Okay, so let's do this twice. Let's do it once kind of quickly with software, and then we'll do it a second time more slowly. We'll use the formulas. We'll go with, by hand, and we'll also make sure we check the distribution requirements. Okay, so just to kind of get the overall idea here, how does this work? We're going to go to GeoGebra, and we're going to go to the t-estimate of a mean. If we want 95% confidence, then we'll put in 0.95. Then we'll put in the sample mean, which is 356.1. Then we also need a measure of the sample standard deviation. So in that set of volunteers, right, some people, it took more to get to the center, right? And some people were able to get to the center quicker. And so not everybody had the same number. And that means there's a spread, right? And so we estimate that spread with the sample standard deviation. Okay, and is the sample size, which is 92. Okay, great. So let's do that in GeoGebra. So let's kind of go from scratch here with this. So we're going to hit the toggle, the 3 dots, probability calculator. Okay, and then if we're doing a confidence interval, we go to the statistics panel, and then we come here to the drop down. Okay, so in chapter 3, we learned about 2 different procedures. We learned about the z-test of a proportion and the z-estimate of a proportion. Okay, so here in chapter 4, we're going to learn about 4 more. Okay, so what's this first one that we're going to learn in chapter 4? Well, we're doing a confidence interval. Remember, confidence intervals are estimates. Okay, we're not doing a hypothesis test, so we can exclude those. Okay, so we're down to here, and so we know it's an estimate. What kind of estimate is it? Well, it depends on the kind of data we have. Okay, so this is quantitative data. It's not categorical. Okay, so it's not proportions we're working with. We're working with means. Okay, so we've whittled it down to these 4. So what kind of sample do we have? Do we have 2 different samples and we're comparing differences? No, we just have 1 sample of people and we're looking at the average, right? So we're down to these 2. Which one is it? Well, if you don't know what sigma is, if you don't know the population standard deviation, then it's going to be the t-distribution, okay? So for our class, we actually never use the z-estimate of a mean, okay? So it's the t-estimate of a mean. Okay, so then we dial in the confidence level. So if we want a 95% confidence interval for the number of licks required to reach the chocolate center, we'll go 0.95 here. Then we put in the sample mean, 356.1. Then the standard deviation, sample standard deviation, 185.7. And then the sample size, 92. And there we go. It's all done for us. Okay, so the confidence interval ranges from 317.6 up to 394.6. Okay. All right, so let's write that down. 317.6 up to 394.6. So there's an interpretation, right? And it's the same format, the same three-part kind of interpretation that we saw in chapter 3. We start by telling the reader what our confidence level is. So we say we are, or there is 95% confidence that the interval between, and then we put in the values for the endpoints. So 317.6 and 394.6 captures the parameter. What's the parameter here? Well, it's a mean, right? It's mu, okay? And remember, we're doing inference for the population, so we don't, at this point, we don't want to say anything about a sample. We want to talk about the population, right? So it captures the true mean, number of licks required to get to the center, for all chocolate Tootsie Pops. Okay, so remember, we're talking about, so you have to keep the population in mind here. So it's the population of all of the chocolate Tootsie Pops that have ever been made, right? So, how many, millions of those are there? Okay, but that, if you could actually retrieve all of those and measure, right, then we could find mu, but of course we can't. So the best we can do is estimate it with a confidence interval. Okay, so it's actually a pretty good estimate in my mind. It's somewhere between about 318 and 395. Okay, so it's actually not a terrible estimate. I think that's pretty precise. So good. Right? And again, it's kind of a quirky example. It's not the most serious of examples, but I think it's kind of fun. All right, so that's how we get it. That's kind of what we're trying to do here. Do you see how it's similar to what we did in chapter 3? What's different? Well, we have a different kind of data. So the upper end point there would be about 395 and the lower would be about 318. Okay, so let's do this a little bit more carefully. Let's use the formulas. Let's do this by hand. Let's also check our distribution requirements. So the t-distribution, it's a probability distribution, and it's based on all sorts of assumptions about where the data is coming from. So let's go through those assumptions. Let's make sure they're met, and then we'll use the formulas. Okay, so we kind of have seen the overall idea here and how to calculate it with technology. Let's go a little bit deeper now. Are there any questions about what we've done here for this problem, about what we're trying to do? Does anybody want to see the GeoGebra again? No? Okay. So what are the requirements? Well, there's 3 distribution requirements. 2 of them will seem very similar. Okay, so what are these requirements? It must come from a random sample, right? Randomness is such a key principle for taking samples, right? It helps us to avoid biases. And so just like with pretty much anything else, when we do a sample here for mu, we need a random sample, or it has to come from some randomized experiment, okay? Secondly, the people, the things, the popsicles, whatever it is that you're looking at, suckers, they have to be independent of each other. Okay, so if you're studying body mass index for people in Utah, you don't want all of your sample to come from like one town in southern Utah or something, right? You want that sample to be spread out across the whole state. And so part of the theory is that the observations that you're drawing are independent of each other. So what's our rule of thumb for that? Well, it's the same as the rule of thumb from chapter 3. The sample size, as long as it's no more than 5% of the population, then the people, the objects in that sample are probably independent of each other. So that part is similar. It's even the same formula. inequality as before. So nothing new there. What is new? Well, this third part is making sure that the sample is large enough. That makes intuitive sense. If you have a sample of 2 people, it's not really going to give you a great estimate, right? So there's a rule of thumb for the central limit theorem to work, and that is either the population is already normal or the sample size is greater than or equal to 30. Okay, so in spirit, it's actually similar to the third requirement from chapter 3, right? That third requirement is making sure that the sample is large enough. Okay, but it's actually simpler than in chapter 3 because all we have to do is make sure that the sample is 30 or the underlying population, the parent population, is already normal. So it's actually easier, which is nice. Okay, so those are the 3 things you have to check for this chapter when you're doing confidence intervals or hypothesis testing. Okay, so let's check those. Okay, and so those will be on your formula card, right? So, on your third exam, bring that formula card with you, or, screenshots, or, write down certain parts of it. Just have those 3 with you, and you don't have to memorize it. So what's the first one? We need to have a random sample. Okay, so do we have a random sample here? Okay, it doesn't actually say. It talks about a survey. A survey is, it's it's a, kind of a good synonym for sample. Doesn't really say anything about random. So here's what I would say. I would probably say I'm going to assume that it's random. Okay. And that's pretty much what I want you to do on the exam. If it doesn't explicitly say random, then I want you to think about it a little bit and say, well, is it obviously not random? I don't see anything here that would make me think it's obviously not random. So I'm going to go ahead and assume that it's random and move forward with the analysis. Then on 2, we have to make sure that the sample size is less than 5% of the whole population. So the sample size here is 92. And so is that less than 5% of all of the chocolate Tootsie Pops out there? Okay, almost certainly, right? So, but nobody knows what that number is except for people who work at the company, perhaps. So we'll do the next best thing, which is to solve that inequality and see what the population size would have to be, right? So the 92 divided by 0.05, and we get 1,840. Are there more than 1,840 chocolate Tootsie Pops? For sure, right? Okay, so the first 2, well, definitely the second one's met. We're gonna give the first one the benefit of the doubt. If you, on the exam, I'm fine with you saying that you doubt the first one, okay? Just as long as you go forward with the rest of the analysis, it's fine. I just want you to comment on it. Okay, then the third is we need either the underlying distribution to be normal or the sample size to be more than 30, okay? And 92 is more than 30, right? So we say n equals 92 is more than 30, so that central limit theorem will kick in. If you remember when we were rolling the dice, right, and we looked at the dots, we saw that those dots congregated towards the center and they became bell-shaped. By the time you have 92 for your sample size, that sampling distribution will be nice and approximately normal. Good, so the conditions are met, which means we can go forward with the formula. Okay, so the formula is here. Okay, so I'd like you to do this by hand a couple of times, and then from there you can move over to technology. Okay, so let's write that formula down and use this. So x bar plus or minus a critical t-score times s over square root of n. Okay, so we're going to have x bar plus or minus the critical t-score times the standard error for x bar. Okay, and the best we can do is use S to estimate sigma. Okay, good. All right, so what was X bar? That was our 356.1. Okay, and then we'll do T star in just a second. S is the sample standard deviation. Okay, so that's 185.7. N, that's the sample size. So that's 92. Okay, so the only thing missing here is T star. So if you're thinking carefully, you might remember, oh, we have a table for Z star values, right? So is there a similar table for T star? Yes, but it's much more complicated, and that's because it changes for every different sample size. So basically, we would have to have one of these tables for each possible sample size, which is just not tenable really on a formula card. So for T star, we will use technology. Okay, so what is the T star required for the 95th percent for a 95% confidence interval? Well, if we want to be 95% confident, we have to go out far enough in the distribution such that we capture the middle 95% of the distribution. Very similar logic to chapter 3. So if 95% is in the middle, then 5% are out in the tails. Okay, so 5% split between two tails is 0.025, right? So we take that 5% and we cut it in half, we get 2.5%. Okay, so we want the T star value such that 0.025% of the, 0.025 as a proportion of the population lies above it. Okay, so we're going to go to the T distribution and we're going to look for this T star value. Okay, all right, so this is what we were practicing earlier. So we go over here to GeoGebra. Let's start from scratch on this. So we go toggle, 3 dots, probability calculator. And we're going to go to distribution. This is the student T distribution. How many degrees of freedom do we have? Well, degrees of freedom equals n minus 1. N here is 92. So the degrees of freedom equals n minus 1. It's going to be 92 minus 1. The degrees of freedom will be 91. Okay, so we go 91. Then we say, well, the area above, we want that to be half of 5%, right? That 5% split into 2. So 0.025. Okay, so that tells us our critical t-score, 1.9864. 1.9864. Okay, so 1.9864. So there we go. It's calculator work at this point. Okay, we just have to pull out the calculator if you're doing this by hand and do some arithmetic. So let's do that. All right, so 185.7, that's the sample standard deviation. We're going to divide that by the square root of 92. Okay. Then we multiply that by our critical t-score. So I'm going to go times 1.9864. And notice I haven't cleared out my calculator, so I'm not going to get any, annoying rounding errors here. Everything is looking good. So that value you see on the calculator there is the margin of error. So we're going to have 356.1 plus 38.458 and minus the same value, right? So we do it twice. That's what the plus and minus means. Just saves us time for writing. So we're going to subtract that off for the left side, and then for the right side, we add. Okay, so let's do that. So if I want to add that value to 356.1, I just go plus 356.1. So what does that get me? 394.6. Does that look familiar? Yep, it's the same as what we found earlier using technology. Then for the left side, for the lower limit for the confidence interval. We go 356.1 minus 38.458. And we get the lower endpoint, right? So 317.6, which is consistent with what we saw before. And so there we go. So I'd like you to do that by hand once or twice. And then after that, you can just use the technology every time for that. Okay. So I want you guys to try one of these confidence intervals. I think it'll come together very quickly for you because you've done lots of confidence interval calculations in chapter 3. The ideas are similar enough that I think it makes the chapter 4 confidence intervals come together much more quickly. So you guys try one. In this exercise on the bottom of 126, we're looking at a study that was done looking at eating habits. Okay, and so we see these a lot because people are interested in health and nutrition. And usually when you see these, it's looking at like calorie intake. This one's a little bit different. They're looking at time spent eating. So that's kind of interesting. I don't know if it's as important as calorie counting and or other kinds of measurements for nutrition, but still, I think it's a worthy question to answer. How much time do you spend eating every day? I mean, so let's say if you have 3 meals a day, and you spend an hour each day, would it be like 3 hours on average? Okay, well, it's probably less than that, I would imagine, because some meals are very quick, right? Or maybe other meals are longer. So who knows, right? And people sometimes skip meals. So if you could talk to everybody in the country and measure the amount of time they spend eating, that would be a quantitative variable, right? So here in this exercise, it's definitely quantitative. By the way, everything in chapter 4 is quantitative. So we're looking at mu. And where is mu? Well, I can definitely, without any doubt, tell you that mu has to be between 0 and 24, without a doubt, right? It can't be a negative number, and there's only 24 hours in a day. So there we go. That's 100% confidence interval. But it's so wide that it's useless, right? So we want to get a narrower, more precise estimate. So who knows what mu is? It's probably much closer to 0 than it is 24 for most people. So maybe there's mu, right? And so to estimate it, we take an X bar, a sample, right? And we take the sample mean. And interestingly, this one was smaller than I would have thought. 1.22 hours for average. And they were looking at sort of, not necessarily adults, but people who are, kind of getting close to full size, right? So 15 years plus. So these are high school age people or older. So, people with kind of, full adult size, more or less, right? So, so that average is 1.22. Now we know because of sampling error that we're going to miss the actual average, right? So what we do is we build a margin of error on the right of X bar. Sound familiar? And then we take the same margin of error and we put it on the left of X bar. Okay, so that creates an interval that we hope will capture mu, right? And so if the interval is narrow enough, it provides us a useful, accurate estimate for mu. Okay, so this 122 is X bar, and that's in hours. And the sample standard deviation is 0.65 hours. Okay, and so the sample size here is 1001. And I want you to create and interpret a 90% confidence interval for the amount of time, the average amount of time that Americans age 15 or older spend eating and drinking each day. So I'll go quiet for a couple minutes and let you guys try this. Okay, and as soon as you get the answer, throw it over in the chat, and then we'll work on it together. Feel free to use GeoGebra on this. If you want to use the formulas, great, but just because of how much time we have in class, I'll be going through the technology. I already showed you the formulas once there. Okay, so give that a try. I'll go quiet, I promise, for a couple. All right, so let's do this one together. So I'm going to jump into GeoGebra here on this. And so let's clear this out. So I'll go to the toggle, the three dots, probability calculator. And then I go to the statistics panel, and then I'm going to come here to the drop down. Okay, so what is it that we're trying to do? What kind of data do we have? Well, we're trying to do a confidence interval, not a test, not a hypothesis test. So these are out. We can come right down to here. It's an estimate. And then we think about what kind of data we have. Okay, this is not categorical data. This is quantitative. So it's a count of the number of hours spent eating. So it's a mean. And so do we have a difference of means? Well, no, that would be like where we have two different samples and we're comparing the two different samples. So it's not a difference of means, it's one of these two. Well, since we don't know the population standard deviation, it has to be the t-estimate of a mean. That's the only thing we can work with here. Okay, so it's the t-estimate of a mean. And we want 90% confidence. So we go 0.9, then we put in this sample mean, 1.22. Seems really low to me, but anyway, 0.65 for the standard deviation. Then we put in this sample size, 1001. And there we go, we've got it. Okay, so about 1.19 up to 1.25. So that's actually a pretty narrow and useful estimate, right? I mean, it's very close to about 1.2 hours. So that's a very usable number, I think. So, so that interval would be 1.19 up to 1.25 hours. Okay, so that's constructing the interval. Now we want to interpret it. Okay, so it's the same three-part interpretation that we've been seeing for a while now. So we say we are, or there is, 90% confident that the true mean number of hours spent eating by the people in the sample, no, by all people in the population. So the population here is Americans age 15 or older. Okay, so we tell people what the confidence level is, then we explain what the parameter is. So in this case, it's the true mean number of hours spent eating by all Americans who are, kind of approaching or adult age already, is captured or contained by the interval from 1.19 hours to 1.25 hours, something like that. Okay, so a couple of follow-up questions on this. What would happen to the confidence interval if we said, okay, well, we can actually live with an 80% confidence interval? So this was calculated at a 90% confidence level. What if we actually decrease the confidence level? Okay, why would we do that? Well, it kind of depends on what industry you're in. Some industries have kind of higher, more exacting standards than others. And so if you can decrease the confidence level, then typically, it's a little bit easier to assemble a sample, right? So what would happen to the confidence interval if the confidence level decreased? Well, think about a net, right? We use this analogy of a net in chapter 3. The same thing holds here. If you're less confident, then that would result in a smaller confidence interval, which in a way is good, right? It's more precision. The smaller the interval, the tighter the estimate is. Okay. What would happen if we decrease the sample size? Okay, so let's keep everything about this sample the same except for a smaller sample size. What would be the case there? Well, if you have a smaller sample size, then you have less information, right? So the only way to make up for that would be to have a wider interval. Okay, good. So that's our first look at confidence intervals for quantitative data. And so are there any questions there about these two that we've done? There's several more in the homework, and I think 2 is enough because you've already done a lot of confidence intervals before, right? In chapter 3, we did lots of them, and now we've done 2 more for a different kind of data. So I think we can actually move on to hypothesis testing at this point, and then you guys will do homework, and then if you have questions in the homework, you can bring them to class or email me about this. But I think 2 is actually enough here. Let's go ahead and move into the other major kind of inference, which is hypothesis testing. Unless you guys have questions, which if you do, I'm more than happy to go over it or even do a different kind of problem if you'd like. Okay, let's move on then. Let's do a hypothesis test using the normal distribution. Okay, so this is on page 127. So New York is referred to as sometimes as the city that never sleeps. Okay, and of course, we don't mean that literally. It just means that it's a very busy, maybe kind of an exciting place full of, people that are, maybe they're working extra or, anyway, kind of restless, right? So let's test that out. Okay, of course they're sleeping, but maybe they're sleeping less than average, right? So I think we all have heard that 8-hour figure before, right? So if 8 hours is sort of the recommended amount, let's see if New Yorkers are sleeping less than the recommended 8 hours per night. Okay, so you see lots of studies about food. You also see lots of studies about sleep because sleep is, everybody is spending a lot of time sleeping, and so it's always on our minds. So you see these studies a lot about sleep as well. So let's do one of these. Okay. So what would the hypotheses be? Well, the amount of sleep you get is it's a count of the number of hours you spend sleeping, right? So if it's a count, then we know we're looking at quantitative data, which means we're we're doing some kind of work involving a mean typically, at least in this class. Okay, so we're trying to figure out what the mean is. So if we put this into the framework of hypothesis testing, we would have a null and an alternative. Okay, so just like before, and this is like the third time I think now you've seen hypothesis testing. So you're going to be very, very good at it by the end of chapter 4. We write down H0 and HA, right? That's the first point. So on the exams, these problems are always worth 4 points, this part. The first point is writing H0, HA. The second point is writing the correct parameter. So that's your second point there, right? Okay, the third point is getting the equal sign and the inequality correct. Okay, so for the null, it's kind of on autopilot. You know that that's always the hypothesis of equality. The alternative is the hypothesis of some kind of inequality. Okay, so so it's going to be a right-tailed test, a left-tailed test, or a two-tailed test. So we look back in the problem for evidence, right? Some kind of indication for which tail, or if it's a two-tailed test, right? So it does say sleep less. So I think that it's pretty clear that this is a one-tailed, left-tailed test. Okay. Less than what? Well, what would be more interesting? That they get kind of the typical, recommended amount, or that they don't. Okay, so I think it'd be more interesting if they were getting less than 8. So kind of the sort of the status quo boring hypothesis is that they're getting the 8, right? So the null is mu equals 8. The alternative is mu less than 8. Okay. So how do we test it? Well, they go out and they get a random sample, right? And they, so they have 35 volunteers, and they either train them for how to record sleeping, or maybe, they come into a sleep lab, right? They have those. So somehow they get these 35 volunteers and they track how much sleep they're getting per night. Okay, so each of those gets a count, and so then they add up all those numbers in the data set, they divide by 35, and they get an average of 7.73 hours. Okay, so 7.73 is not equal to 8. It is indeed less than 8. But is it enough below 8 that we're convinced by X bar here? Okay, so it's only about 0.2 hours below 8. So maybe we're not convinced. Okay, so, or maybe you are, right? Well, how do you get convinced? You need a p-value, right? And to get the p-value, you need a distribution. So let's do this a couple of times. Let's do it kind of quickly once using technology so you can sort of see the general idea. Then we'll do it more carefully, more slowly by hand, and we'll go through all the details. Okay, so the quick way is to jump into GeoGebra and do the hypothesis test. So let's do that. Let's kind of do this quickly, knowing that we're kind of sweeping some details under the rug for the moment. Then we'll go back and we'll look at the details more carefully. So we go to GeoGebra, we hit the toggle, the 3 dots, the probability calculator, and we go to the statistics panel. We go to our dropdown. Okay, at this point in the semester, we've actually covered several of these different inference procedures. So it's going to be a bit of a process of elimination to figure out the right inference procedure. Okay, so what is it that we're doing? Well, we're doing a hypothesis test. We're not doing a confidence interval. Confidence intervals are estimates, so we can discard all of these, right? So it's going to be one of these. Okay, so then we think about the type of data we have. So we said that sleep amount is quantitative. Okay, so we're up here with the means. It's not a proportion. So what kind of sample do we have? Do we have two different samples and we're looking at a difference between the two? Or do we have a single sample? Yeah, we just have a single sample, right? So we've narrowed it down to these two. Does anybody want to guess which one it is? Is it the z-test for a mean or t-test for a mean? What do you guys think? Let's see here. Exactly, Julia. Perfect. Yeah. And why is that? Well, because we don't know what the population standard deviation is. If we did know the population standard deviation, then it would be z-test of a mean, but we don't. Okay, so pretty much in this class, anytime you're doing inference about mu, it's going to be the t-distribution. Okay, so we never in this class use the z-test of a mean. Okay, so it's going to be the t-test of a mean. Okay, so the null value is the 8, right? The alternative is less. Then we put in the sample mean, which was 7.73, and we put in the standard deviation, right? Because some of the people in that sample are going to sleep more, others will sleep less. So there's some spread. We measure that with a sample standard deviation. Then we put in our sample size, it's a fairly small sample of 35. And there we go. Okay, so we have our test statistic. Okay, so in chapter 3, the test statistic was the z-score, but now we're in the t-distribution, so our test statistic will be the t-score, and that is negative 2.07. And what do you suppose this p is? That's the p-value. Okay, so we have a p-value of 0.0228. So all of these hypothesis tests that you do will come with, will have some resulting p-value, right? And you know what to do with that. You take p-value, you compare it to alpha, and then you decide if you're going to reject or fail to reject, right? So let's write down those two numbers. The test statistic is t equals negative 2.07, and then the p-value is 0, just coming from the software, 0.0228. What do we do with that? We compare it to alpha. Okay, so alpha varies from industry to industry, and so on the exam, we'll be sure to give you that. If for some reason I forget to put that in on a problem, then you can choose your own alpha value. A typical one would be 0.05. Okay, so since the p-value is less than alpha, we know what to do, right? We're going to reject the null. Okay, when you reject the null, you're rejecting because there is sufficient evidence to support the alternative, right? So this is our formal conclusion, but it's not really the last step. The last step is where we take that formal conclusion and we put it into language, more plain language, not necessarily like dumbed down language, but language that anybody who's interested can understand, right? So it still is a little bit stuffy language, but at least it doesn't refer to like p-values and alternative hypotheses and stuff. So there's sufficient evidence to conclude that the alternative is true, right? But we don't say alternative is true. We say that New Yorkers sleep less than 8 hours per night on average, right? So New Yorkers sleep less, and we should probably say on average, sleep less than 8 hours per night. That's what the alternative is, right? That the average number of hours slept by all New Yorkers is less than 8 hours per night. So what do you think? It's kind of similar to what we've done before, right? What we were doing in chapter 3. So it also, I think this hypothesis testing, now it's like the third time you've seen it, it really starts to gel quite nicely. If it hasn't already, then I think as long as you've been doing the homework, this hypothesis testing idea will really come together for you. Okay. Let's go back and do it again now that we have an idea of what's going on here. and the final answer. Let's go back and do it again, but this time we'll go through the steps a little bit more carefully. We'll look at the distribution requirements and just look at the details a little bit more carefully. Any questions? So if we're doing this for real, then we need to check the requirements, right? So any good analyst, researcher, if they're using these methods, they will check their requirements. Okay, bad researchers, bad analysts will skip over these requirements, and then later their results might be overturned, right? So we want to check the requirements. Okay, first of all, we need to make sure that we have a random sample. Okay, so and what are these three requirements? Well, they're the ones that we already looked at, right? They're right here. Okay, so we have a random sample, we have independence, and we have a large enough sample, right? That's the three requirements. So do we have a random sample here? No, it says random sample. Yep. Okay, so we'll say says random. Okay. So on your exam, make some comment about it. If it doesn't say random, then say you can assume it's random, or if you're convinced it's not, then just say it's not random. But go ahead and just go forward with the analysis anyway. So then number two, these are presented in a different order than in the lecture in the formula card. Okay, so let's skip down here to number three. Number three is saying that we get 35 people that are independent of each other, right? You don't want 35 people who all work in the nightclub industry or something, right? You want 35 people that are representative of the whole population. So the way we do that is getting a random sample that's less than 5% of the whole population. Obviously, 35 people from a city of 7 or 8 or more million people is less than 5%, right? So, but I do want you to be able to do this calculation here. And you've done this, if you've done the homework, you've done this at least a dozen times by now, I think, right? So that should be easy for you. 35 divided by 0.05. So 35, whoops. 35 divided by 0.05, 700. Okay, so are there more than 700 people in New York City? Of course. Okay, good. Then number two, we have to make sure that either the population is already normally distributed or the sample size is large enough. It doesn't say anything about sleep being normally distributed, but that doesn't matter because the sample size here, 35, is more than 30, so we're good. So what does that mean? It means that X bar, it means the central limit theorem will kick in and X bar will be normally distributed. Okay. So the very underlying distribution is a normal distribution. However, because we don't know what sigma is, the parent population's standard deviation, we have to estimate it with S. So that sends us over into the t distribution. Okay, so the t distribution does resemble the normal. I mean, it's a bell-shaped curve, right? So the mean is 8. The standard error is 0.77 over square root of 35. Okay, so that's estimated at 0.13. So if you're taking samples of size 35 and you're calculating the average number of hours slept, it'll bounce around by about 0.13 hours. So what sample values would be surprising? Well, anything where the p-value is less than the significance level. Okay, so you're going to get your sample. That's going to be X bar, and in this case, it's a left tail test. So our p-value will be the area there in that left end of the distribution. So what sample values would be surprising? Well, values where the associated p-value is less than the significance level, which in this case is the 5% significance level. Okay, so we didn't quite finish this one uh, the second time through, so we'll pick back up with this a week from today, right? Remember, no class on Thursday. We have a day off for fall break. Actually, we have 2 days off, but only one of those is during our class. So let's stop here. You guys have any questions about anything that you want to go over? If you didn't receive your exam for some reason, let me know. I believe I've graded all the ones that were sent to me. So if you didn't see your exam there, go look for it again. And then if you don't see it, let me know. And then look at that key that I posted a few days ago and go over your exam. Sometimes I make mistakes occasionally grading. So if the points don't add up correctly or you think you deserve some more partial credit, let me know and I'm more than happy to revisit the exam. So, okay, guys, have a good fall break and let's come back from fall break with just a few weeks left in the semester and hopefully kind of re-energized from a break. And then I'll see you guys on Tuesday. Take care. Okay, thanks, guys.